Okay, so welcome everyone. Tonight we're going to discuss pulsar timing arrays for gravitational wave analysis. That's a mouthful, but what it basically means is if you know the time of arrival of the beam of 30 plus pulsars, and you monitor their arrival very closely, like to the few nanoseconds level. When you see a disturbance move across your array of pulsars, it's probably due to a gravitational wave passing between you here on the Earth and whatever pulsars you're timing from. So we'll get into all the details of why do we need that, and does it work, and what have they found out given that they've started playing with this stuff. But as usual, first we'll do the news. Webb is almost out to the point where it will fire its rocket to put it into its L2 halo insertion point. It's kind of like a golf putt. You want to get as close as you can without going too far, because remember, there are no rockets on the top side of the James Webb Space Telescope, and they don't want to turn it around backwards to face the sun. So they can get as close as they want to their insertion point, but they dare not go past it. So on Monday, January 24th, the current plan, although they have a little flexibility in it, is to do a thrust firing to tilt. They'll actually be doing the thrust firing and their momentum wheel turning to bend it into the L2 halo orbit. And as I mentioned last week, the halo orbit is not a flat ellipse. It's actually a curve. And here it shows a flat ellipse. This is not accurate. But it'll actually be a curve. So the top of the ellipse will be facing farther away from the Earth than the bottom. But instead of it being a disk on an angle, it's actually a curve on an angle. But that's the next tricky thing they're doing. They actually moved all the mirrors out from their stable, secure points that they placed them in for launch. They moved them all out 12.5 millimeters to basically their 0 point, so that they can begin tilting the mirrors to converge the beam. So it's like the world's worst collimation. Not only do you have a primary and a secondary you have to collimate, you have 18 primary segments you have to collimate. So they'll do that once they get into their halo orbit, because the presumption is there might be a little bit of vibration as they fire the rocket to tweak them into their halo orbit. But we'll see how that goes. We'll probably know whether the orbit insertion worked or not by Tuesday morning, because it fires off and on for an extended period of time. But as usual, you can go to that blog page. You can go to this page, which the L2 insertion burn, also known as mid-course correction burn number 2. They had a 1A and a 1B, and this is 2. Funny, this page doesn't tell you the exact date and time at which it will occur, so it's just a planning page. But you go back to the blog page, and it will tell you exactly when they expect the burn to start occurring. And then once they get into L2, the next step is, hey, we're orbiting at L2. Well, what's after that? I don't see anything else in the schedule, but they still have mirror convergence to do and testing the rest of the instruments in both imaging and spectroscopic modes, with and without slits on their spectrometers. So there's a bunch of stuff left to do before they can start doing real observing. And the first light real observing will actually be just some test images. It won't actually be scientific observing. And they'll be doing test observing for about 6 months before they start actually processing the research proposals.
I put a video on the chat showing the orbit.
And next week we'll talk about orbits. So the United Launch Alliance launched one of their last remaining Atlas V rockets to loft 2 U.S. Space Force surveillance payloads to geosynchronous orbit on the 21st. So
what's a surveilling?
It's on a you don't need to know basis. What they're supposedly going to do is use a pair of satellites to monitor other satellites. And as usual, it's like, okay, here's the ULA promotional page of the launching of the Space Force satellites. Like, okay, that's all really good, but what about the details? Let's get some details. So you can actually go off to a different page. This is the joint-forces.com. This is some guys that, like to go get details on secret things that probably shouldn't be publicized, but are. So here's the two satellites. They're in geosynchronous orbit. They're made by Northrop Grumman. They're part of the GSSAP, the Geosynchronous Surveillance Astronomy Program or something like that. And this is mission number 8. What happened to mission number 7? It didn't go well. That was the one that they got everything up, but the second stage, was it? The second stage didn't burn quite right. So the satellites never achieved geosynchronous orbit. So just draw a line through 7. This is 8. Okay, and everybody's talking about the James Webb Space Telescope and the other things we have that are already up there and are going to be up there in the next few years aren't getting enough PR coverage. So they created a simulation of what the Nancy Grace Roman Space Telescope should be able to see within its field of view. Pretty pictures are always interesting to look at, like, okay, is it actually going to have this in the background? No, that's just a collage. It will be taking pictures of large fields of view in infrared. Like, well, why is the picture in color? Because it looks prettier that way. But so the Roman telescope will go up in the mid 2020s, I guess it's mid 2020s. So 2024, 2025, something like that. It will not be at L2. It will be in Earth orbit. It'll be in a, I think it's ammonia orbit. But you can see it has sort of shielding around the telescope, around the instruments. It's got a sun shield on the front, so the sun can't peek over the corner. And it's got solar panels up here. So it has to kind of tilt backwards a bit to get the sun on the panels, but it blocks out the sun with this giant tongue to prevent the sun from getting into the telescope. Now, the Roman telescope is smaller in diameter than the James Webb Space Telescope, but it has a different set of instruments on board. So you might ask, well, why didn't they just make the Webb telescope better? And why would you need to spend money on the Roman? Well, the Webb telescope has very small field of view because they're targeting things like exoplanets. The Roman Space Telescope has a very, very large field of view because they want to do population studies of galaxies. And it's in infrared because they want to study early galaxies, much like the Webb is doing. So if you remember me showing you the field of view of the Webb telescope, they project the light from the front of the telescope onto a whole bunch of sensors, and the sensors can all take different pictures at different times. So what they've done here is said, well, if we have all these chips and these chips take up, different pieces of the sky and you can glue them all together except for the gaps between them, then compare it to like the Hubble deep field, the Hubble ultra deep field, and then this is what the Roman can see. It can see a whole lot more of the sky, but it's seeing it using a multitude of chips. So even though it can see a wider area, there's a lot of stuff lost. Like, hey, we lost a galaxy here between these two chips. We lost another galaxy over here between these two chips. how many galaxies under longer exposure did we miss? Well, nobody's going to make you a 24 gigapixel imaging chip because there's no commercial demand for them, and it would just cost too much taxpayer dollars to build a one-of-a-kind chip. So they send multiple chips up and kind of glue them together. And if you want more details on it, there is a NASA Goddard Space Flight Center page, lots of pretty pictures for what the Roman's going to be able to do. And here's that comparison image. Anyway, that's the Roman. And there is a SpaceX Cargo Dragon capsule that's currently docked with the International Space Station. But because of foul weather in the landing zone, they delayed the departure from the space station until tomorrow. So tomorrow at 10:40 a.m., if you're going to be up that early, I know I'm not, I'll watch it on YouTube afterwards. You can watch the arrival of the cargo ship.
Most likely when they bring something back as experiments.
Yes, it's usually scientific experiments. There will be no live coverage of the splashdown. So they'll be talking about it and pointing at pictures, and the actual splashdown, there will be no live coverage. So I'm going to guess that's NASA's choice, not SpaceX's, because SpaceX usually does live coverage everywhere they can. So it'll return nearly 5,000 pounds of science. I didn't know you could weigh science. It's 5,000 pounds of science. They're going to be sending back the cytoskeleton to understand human cell changes and signaling in microgravity. Oh, and they've got a 12-year-old light imaging microscope that is being retired after more than a decade of use aboard ISS. The Light Microscopy Module, the LMM, that's what they're sending back. Anyway, that's one of the things they're returning. We've had our first aircraft grounding based upon local weather. The Mars Ingenuity helicopter wanted to fly on another mission, and there's a nearby dust storm. So they are going to keep it grounded until the dust storm clears. It's done what, 18 flights now? So I guess they aren't taking as many chances as I thought. The air pressure being so low on Mars, and right now it being summertime, the air pressure should be even lower. Yes, this would be flight 19. Let's keep Hubble in the news. So meanwhile, you've got other space-borne instruments and instruments that aren't even launched yet trying to steal Hubble's thunder. Hubble says, take that. I found a black hole whose energy beam coming out at the pole of the black hole, apparently it's tilted to the plane of its galaxy, is actually compressing gas and dust and creating a star-forming region within this dwarf galaxy. So they're pointing it out as, first of all, it's from Hubble. Hubble back in operation again. But notice that they didn't tell you when the picture was taken. I always find that interesting. Which instrument did you use, and when did you actually take the picture? I don't see anything here that says that. But it's a galaxy 30 million light years away, and the star-forming region is 230 light years away from the center of the black hole, the center of that galaxy. Here's the picture you think it took. Here's the picture it actually took. It's a lot less pretty, but it's the contradiction in terms. Normally, black holes are known for gobbling up and shredding stars, and here we have a black hole whose jet is actually creating stars by creating a star-forming region.
Our own galaxy has something like that.
When we were a quasar, yes, but since we're no longer a quasar, we have star-forming.
No, you can see a star-forming region around the black hole. It's a ring. It's the pictures that show on Sophia. That is a region that forms young stars near to the black hole.
Well, what's that? That's got to be things on their way into the black hole compressing, because the black hole itself would be pulling in one direction. But yeah, I remember
some
seeing
of those gases get compressed and they collapse to form new stars. But of course, it depends how short-lived, how big those stars are, and how close they can get. And then, they they get stretched out until they lose their
They get
hydrostatic
shredded.
equilibrium.
They get shredded by going past the event horizon. Yeah. Although I found out that there's a new thing that's out beyond the event horizon that's actually got a recognized term for it. We'll discuss that. Meanwhile, I've got 3 articles here that I found interesting because they're quantum physics.
Yeah, entanglement. Good.
And things get entangled.
Yeah.
So I always like the headlines because I know that's not what they're actually doing. Long dash range, quantum entanglement measured at last. Well, it's not only been measured, it's been measured and then confirmed by other people. So they should say long range quantum entanglement measured and confirmed. So what do you think long range means?
Centimeters?
But it doesn't matter. It could be forever. You're very far.
Okay. Quantum is, less than the diameter of atoms. So long range could be a few atoms away. And that's literally what it is their definition of long range is we went from quantum to macroscopic, which is still micron level microscopic. So that's what they did. They actually arranged to use the Google quantum computer to change the state. I think they changed the spin state of 2 particles, and then they separated the particles out. Now, by separating them, they moved them a few atoms away. How do you do that at that small a scale? Wow. We have to go and deal with my favorite items here. Now, they're showing it as if they move the atoms, the quantum entanglement from here to here. That's not really the case. They didn't even move them from here to here. They moved them from a place in here to a place in here. So you've always got to be aware of this. And you can dig down further if you know how to get to the U.S. National Institute of Standards and Technology, NIST. I know guys who work at NIST. So anyway, that was to define, well, what scale was the entanglement? But then the best part, the part that sort of struck home with me is, how did they move the nanoparticles around? Because a quantum computer is down near 0 Kelvin bath of liquid helium, super cooled helium. They used laser. Now they made them green and red here, but I think they were both red. They used one laser to push the particles into a confined area. Then they used another more focused laser to act as kind of a cone that contained them. Here's my favorite frustum shaped containment vessel for photons. So they were using radiation reflection pressure as a quantum tweezer to hold these particles where they wanted them. So we have 3 things going on here. Yes, we're doing quantum entanglement. Yes, we've got the farthest separated things that we've ever had that were still quantum entangled. That just means that they set the spin and the spin stays that way when they separate them apart. And if they change the spin on one, that changes the spin on the other.
Right.
And they did so using laser beams, and they didn't even need to put them on the heads of sharks. And that was what I had for the news for today.
That's plenty.
I thought it was a lot. I doubled up and had a couple. If you got the email, I have a couple of links for each one of them, because sometimes it'll be the PR telling you about some spacecraft, and then you go to the NASA link and get all the details on the spacecraft.
Monroe, I posted the animation of the James Webb orbit. It's interesting.
Is it the NASA animation?
Yes.
Okay, so yes, the JWST is in a Sun-Earth L2 halo orbit. So here's the Sun, here's the Earth. That's the basis for your orbit. And then if you go out beyond the Earth, beyond the Moon, you get to Lagrangian point 2, and it's going to do an elliptical orbit of that.
Yeah, this is what I saw. Yeah.
It's a nice animation, but I'm not sure that it correct. It looks like it's a flat
The
ellipse.
ellipses is just a little bit, I think the angle is higher from
Yeah.
what we saw,
Yeah.
but you know, it is an animation.
Well, it gives you a better feel for the fact that it's not at L2, it is in an elliptical orbit about L2. And it also
And then
shows
take a
you,
look at where the telescope's pointing, is always pointing in the same direction. So basic, it's gonna image just the North Pole, not the South.
no. It will never turn around and face the sun, but it can rotate around its center point. The entire spacecraft rotates around its center point. So it doesn't always face downward, but its orbit is naturally with the telescope pointing downward. It can rotate the telescope. The entire spacecraft rotates courtesy of the momentum wheels, so it can turn it around and face the northern part of the sky or the southern part of the sky. I'll bring out my paper model. So the picture is showing that it is facing up like this.
Yeah.
But it can actually rotate the entire spacecraft through 360.
Oh, I didn't know that.
Yes. And
And
the telescope does not turn within the sun shield. It is fixed. So if they want to, instead of the telescope pointing up, they want to point it down, they rotate the entire telescope to point down. Now, off angle, they cannot do that. They cannot do this because that would point it at the sun. So what they can do is, I'm going to turn it 90 degrees, but remember, it can't face the sun. They can wiggle it a little bit. So it can do 5 degrees this way and 5 degrees this way. And I think it's 13 degrees this way and 13 degrees that way. And that's its only latitude of movement. So if you think of it as, if this was a spray painter instead of a reflector telescope, and you turned it on, how much of the sky would it be covering? Not that much. And then you say, well, it can tilt a little this way, a little this way, a little this way, a little this way. And you take that wider spot and now you rotate it up. So you create a swath with it. Notice that it can never do that. It can never go out from it. So how do you get pictures of that part of the sky? Because, as you can see, it's orbiting in an ellipse. So that's how we'll see other parts of the sky. But the L2 is in synchronous with the Earth orbiting around the sun. So it will go around like this, as well as being able to rotate this way. So there definitely are areas where it will not be able to ever see, but there are other areas that it can see, but only during certain times of the year.
So for this rotation, it uses just the gyroscopic wheels, or uses
No. What it actually does is, if you split the ellipse vertically into two sections, the upper section and the lower section, when it's going one direction, it uses the momentum wheels to arc itself. When it's going the other direction, it has to do a brief firing of its rocket motor to push it back, and then it uses the momentum wheels to steer it. So that's part of the life duration of the telescope. They know what size they want the orbit to be, and the orbit maximum is almost the size of the sun. It's a little smaller, but it's almost the size of the sun. So it's way larger than the Earth itself. So that's this giant ellipse that it's going to be doing. It takes 66 days to do the entire ellipse.
No, my question is, when it turns like south, north, north, south, it uses any
just the momentum,
or just the stabilization?
No, that's just a momentum wheel. The problem is that the momentum wheels have a maximum speed. So if the telescope is arcing up this way, they're already using the momentum wheels to gain a certain curvature of the orbit. And then if you wanted to turn the telescope like this, you may not have enough momentum left at the to get up to the maximum spin rate of the momentum wheels. And what you'll do is you'll spin it a little bit, and then you'll let it spin down, and then you'll fire the latitude thruster to rotate it like this. And now your wheels are available for full rotation again, and then you'll finish the rotation up. So depending upon what you're observing, you may need to use the momentum wheels and the rockets, because the momentum wheels have a top speed. And once you're pushing against the inertia of the spacecraft with the momentum wheel, when it reaches top RPM, you're not going to go any further. It's just going to sit there. That's the Achilles heel of momentum wheels, that and their bearings wearing out.
Yeah, that too.
Yeah. Although I think it was about 12 years ago, they found the reason why momentum wheels were wearing out so fast. Turns out it had to do with the materials and the creation of an electromagnetic flux between the bearing components. So it would literally pull the shaft more in one direction magnetically, which would cause it to wear more there than on the other part of the shaft, which caused it to wear the bearings out. And they did a little chemistry, a little metallurgy, and changed the metals that they used in the outer shell of the momentum wheel bearings, and now they should be good for much longer. I don't know if they had the newer model ones on the last Hubble servicing mission, but I know the Webb bearings are of the longer duration variety. That's why they're not concerned about having to go out to the Webb to replace its momentum wheel bearings. I saw a prediction by Dr. Becky on YouTube, where she was proclaiming that the Webb might even last as long as 20 years.
Yeah, I don't know. I have my doubts about moving parts.
No, I have my doubts about fuel, because they have a fixed amount of fuel.
Yeah.
And they can't do everything with the momentum wheels, and they positively need the fuel to shape the elliptical orbit about L2, because it's not a stable orbit. So they will be periodically consuming a continuous amount of fuel. And when that fuel tank starts to run low, you're done. So unlike the Swift Space Telescope, which was another infrared telescope, Swift used liquid helium to keep things cool. The Webb uses liquid helium, but it has its own cryo-chilling refrigerator. So it can keep the liquid helium cold without having to worry about the liquid helium being under such pressure that it all leaks out in 5 years, which is what happened to the other infrared telescope. Is that 5 good years of cold, and then 5 years of warmed down, and then it was done because it ran out of fuel. But it's still out there. Spitzer is in a heliocentric orbit. So it's roaming around the sun. That's the best way to describe it. Do we have another video here? No. Hey, that's a picture that I used. Keeps the hot side hot and the cold side cold. Oh, here's a thought. Let's see if we have a picture that will show this. Yes, there we go. So you see that the moon orbits the Earth, and that the Webb is out here at L2. The sun, during certain positions of the lunar orbit, will be reflecting additional sunlight onto the bottom of the JWST. So as the moon is over on this side of its orbit, and as the moon is over on this side of the orbit, I would like to see the data to see if the bottom side of the JWST gets warmer. That would be interesting data to see. So about a year from now, when the data is made available to the general public, I'd like to remember to go back and look at that and see if the additional reflection of sunlight from the surface of the moon onto the bottom of the JWST, because remember, this is showing the elliptical orbit as being small. The elliptical orbit is actually all the way out to here and here, because this is not much larger than the Earth, and the Earth is kind of a supersized compared to the sun.
It's probably impractical
The
to make.
temperature data available for the hot side is public, so you can do a compilation of the data and see if there are.
Yeah, but I'd have to do the compilation myself, and I would just rather, give me a certain amount of time, probably 120 days after it's been in its L2. So it actually did two L2 orbits and several orbits of the moon around the Earth. And that would be about a 6-month period of the Earth orbiting the sun. And then look at all the temperature data on the bottom side and see if you can see a repeating pattern.
Because the orbit of the James Webb Space Telescope is higher and lower from the orbit of the moon, I don't think there will be any effect on it. Maybe there's probably it will be some kind of effect during the closer orbit of the sun and the farther of the sun, the ellipses of the Earth.
You mean the aphelion and the perihelion?
Yes.
Yes. Yes, you do have a point there that when the sun is closer to the Earth, so when the
during the winter.
Yeah, during the winter time for North America, when it's really hot, when the sun's closer, that could increase the brightness, but then you'd have to have the moon in the right place in its orbit around the Earth, and then you'd have to have the JWST being about in the center of its orbit, either on the lower side or the upper side. But I think it'd just be interesting data to look at. And then if it does actually correlate to something, then I can send the email back to Will and go, look what we found. So I'm still looking for anybody that is willing to either naked eye, binocular, or telescope, see if they can spot the James Webb Space Telescope, preferably after it gets into its L2 halo orbit on Monday. I just want to determine its true brightness. So it would be one thing to spot it. You can use heavens above to spot it if you want to. But I'd also like to pick out a handful of stars around it that you can get the name of and get their magnitude, so you can do it's brighter than this but dimmer than that kind of thing to get a good measurement of what the brightness of the JWST is going to be. Okay, and I did post on the Broward Astronomy YouTube site the business of androids. I finally got that done and put that out there. And then also this week I posted to the YouTube site the access and use of scientific research data, put that video out there. And one of the suggestions when we were recording that was there's a lot of information out there about orbits. Do a session on orbits. So tonight we're going to be talking about pulsar timing arrays for gravitational wave analysis. But next week, we're going to be talking about understanding two-body orbits. A two-body orbit is you've got one thing orbiting another thing.
The famous two-body problem.
It's a two-body problem. It's a problem for somebody with two bodies. Now, why do I want to confine it to two bodies? Because once you get to n bodies, it takes supercomputers. But does anybody recognize a popular science fiction three-body problem? Think about a planet with two suns. Star Wars, Tatooine. Okay, none of you follow that. We've got a Star Trek crowd here.
You could say the Earth, because the moon, the sun, that's a three-body problem.
Yes, if you were evaluating the effects of the moon, the Earth in orbit around the sun, that would be a three-body problem.
And the other one, it could be a Tikasi and Tikut.
A what?
Tikasi and Tikut. Vulcan and its moons.
Oh, okay. Yes, Vulcan has
So,
two moons.
from what I read from people who write like fan fiction, Chikut, it's the moon. It's very close and is very big. Like,
That's what makes
you
all the
know,
Vulcans tall, is the gravity of their very close moon stretches them.
but there are other fan fiction that says the Vulcan doesn't have a moon. So it depends who writes it.
Yes.
But
Well,
they have names. It's,
what do they
the
call it?
planet
It's
of
not,
Vulcan is Tikasi, and the moon is Tikut.
it's not called dogma. It's called, oh, canon. It's not canon. Yes. It's not other towel makers either. Canon. Okay. Did I miss any news items that people saw in the news that we might want to discuss? I had a lot of them. I deliberately left out a couple. They were
Yeah,
more
which ones? What?
political than you know. I tend to leave those out because they're on agendas. You know, they've got an agenda that is a reason why they're promoting something. And like, well, first of all, they did that observing 3 years ago, so I don't think that's news for today. Or that's something they're theoretically going to be launching 20 years from now. You're just looking
So
for budget. You're looking for budget money.
the only news that I have is like a bit urgent, is like, if anybody else then, you know, our crowd here is watching that is a professional astronomer or a student of astronomy, you have to the end of this month to put your proposal for observing on Sophia and TikTok.
Yes, but you need to be a credentialed scientist to do that. Yes, there's a little hurdle you have to cross in order to submit a proposal. But I know what's happening. Sophia has a certain amount of flight time that they want to book every year to justify their cost. And in order to do that, they have to have a certain number of research projects that require Sophia for their observing. And the problem you're running into is, okay, you've got the James Webb, you've still got Hubble, you've got all these new ground-based telescopes on very, high places in Chile opening up, and like Sophia is just not getting a lot of, tender loving care time. So they're not getting the number of proposals to fill their airtime. So they're kind of begging for proposals.
Yeah,
I think.
And the last post they did, they were doing some data to confirm the observations from Venus,
Yes.
from the amino acids found it, and some of the metabolites, that it could be a signal of life under the clouds of Venus. So they're doing just like they did for the New Horizons. They are confirming observations.
Yeah. Well, that's something that Sophia has a long track record of doing, is if other instruments are not available or they've already gone by or whatever, and you just want something to give you that second, yep, confirmed. Sophia is good at doing that because you can task Sophia far quicker by years, especially if it already has the appropriate instruments, than launching a new mission to confirm it. Think of the number of years between the Galileo probe going to Jupiter and finding some additional moons, and then having to wait for the Cassini probe to go past Jupiter on its way to Saturn to confirm them. Well, if you've found something out and you would like to have confirmation, if you can schedule that through Sophia, your confirmation is going to take many years less time and less budget money to get it approved. But that's a value, and you first have to recognize that Sophia has unique values. Sophia can see deeper into infrared than can the James Webb Space Telescope. But it's out in space. No, it's lower frequency, longer wavelength, because the sensors are on board an airplane, and you can make newer, better sensors. And it does fly above 90+% of the Earth's moisture. So that, opens it up to infrared observing.
And one of the other news, I don't know if you caught it, is Curiosity is observing some strange signatures in carbon. So they are doing like data and looking at the carbon and see intriguing. That's the word. The word intriguing carbon signatures. So
Yes.
that will be an interesting post to look.
And I posted that one about 3 weeks ago. That was one during the first one we did in 2022. I did mention that. But as usual, let's be real careful here, because we don't want to claim that there's life on Mars until it, walks up to us and hits us in the head with a hammer. Or we see in a microscope little things squiggling around, or it's got to be real life, not none of this fake life stuff. It can't be a chemical signature of life. It's got to be real life. So the Viking landers detected signs of life that were chemical in nature. Curiosity has done that. Perseverance has done that. So they're all creeping very closely to, look, we've found carbon chemistry that is found on Earth only where there's life. Does that mean there's life on Mars? No, of course not. If you always want the answer to be no, you can find a way for the answer to be no. If you always want the answer to be yes, you'll take any slim evidence to make the answer yes. So both camps have a little bias towards it. And I think the best thing is. Yes, Joanne.
We have these chemicals. Now, I gather, because I'm a life form, I leave these chemicals too, right?
Yes.
Okay, but bacteria that's much, much smaller than me also leaves those chemicals, right?
Yes.
So these chemical amounts, I would leave a lot more chemical than a bacteria, right?
Yes, but there's billions times more bacteria than there are you.
Yeah. Okay, so you're saying then when then that messes up my thought.
Yeah. I knew where you were going with this one. And okay. Yes.
What was it going with it?
Yes. If there is a precursor to life that they've detected on Mars, and they haven't detected it in a physical compound, a substance in quantity, they've only detected it spectroscopically. It can be, parts per million or parts per billion, but that's how much they detected in the sample they took. And if the sample they took is, smaller than the point of a pencil, and they found parts per million, if you expand that out to a uniform sample.
It's not the quantity of carbon. It's not the quantity of carbon on rocks, but it's actually the isotope composition. So they're finding a little bit higher percentage of lighter carbon than it was supposed to be. The normal, proportion of those isotopes in the solar system. So this could be a signature, but the same way that we point out to very old rocks here on Earth, you cannot really confirm, because physical, chemical processes that can cause it to actually precipitate more of the heavier carbon or more of the lighter carbon, depending on what kind of water, what kind of slug, what kind of bacteria mat you have it. So they need more data to confirm. But what is intriguing is that it uses the proportion of lighter carbon is like, whoops, hello, a signal. Same thing that the geologists do here for very ancient rocks. This could be. You cannot point out when you don't have enough data, but it's kind of cool, because how can you make sense of that? So they are not saying that is life on Mars right now, because Mars is stripped from its protection from the atmosphere and also the protection of the magnetosphere. So all the surface could be dead. It's sterilized. But when they look at rocks that were sedimented when you have water on Mars, that could give a signal that some of those rocks have some bacterial match that frozen in time. You can verify the isotopic composition.
But from the presence of hydrogen, they've concluded that at the bottom of Valley Marineris, there is slushy water mixed in with mud. And if that's the case, then the whole potential of sterilization of the surface is true, but the sterilization in the bottom of Valley Marineris may not have taken place. So yes, we need a new kind of probe that will go into the bottom of Valley Marineris and have an antenna that points up to the edge of the valley, and then you use a relay satellite there to get to orbit. And yeah, it's time to come up with a new kind of spacecraft for Mars, one that might really find something, as opposed to make sure you don't pack the correct kind of instrument that would actually see something. I've always found that to be kind of interesting. It's like when somebody says, I left that in my other pants. Yeah, when you know you were going there, why did you leave it in your other pants? Well, I didn't want to have to do that. So in this case, I wanted to make sure there was no way in hell we could actually confirm it. So we don't have
what happens is that they don't let you go into the airplane with whatever you want to carry.
Yes, yes. Okay, any other news items before we kick this thing off? So welcome once again. Tonight we're going to be talking about pulsar timing arrays for gravitational wave analysis. It sounds like a lot of gobbledygook words, but we'll get into the explanation. I think you'll find it, not overly complicated. You can narrow it down to almost straightforward. Okay, a what for what? So at the end of their lives, some stars collapse into rapidly spinning neutron stars. Neutron stars emit an opposing pair of jets of high energy significantly in the radio band. Due to their spin, they act like short period celestial radio beaming lighthouses. So I'll at this point pull out my Jodrell Bank audio sound, but we're not getting so much into what pulsars are. Just suffice it to say, if a pulsar were beaming radio light at you, what you would see is the beam would come around, smack you, and then go around and smack you again. And it would have a very defined period based upon the spin rate of the pulsar. So now that you know that you can use a pulsar for a reliable, timely pulse of energy, we can use that to detect things that interrupt that. Gravity waves or gravitational waves are distortions in the fabric of space-time. Literally, space is compressing or stretching. That's what a gravity wave is doing. They're similar to ripple waves on a pond in that they have waveform characteristics like wavelength, the distance between the ripple crests, and they have amplitude, how high they go. Gravity waves have been studied at lower frequencies, lower occurrence rates, longer wavelengths using the Ligo and VIRGO gravity wave observatories. They use a pair of very long, multiple kilometers, single-digit multiple kilometers, underground tunnels, and they're oriented sort of in an L shape, 90 degrees to one another. The tunnels contain vibration, isolated, evacuated metal tubes. It's always a series of tubes, isn't it? Through which they split a laser beam at one end, at the joint of the L. They split the laser beam and it goes down each one of the tubes, reflects off of mirrors that are exactly at the same distance down each tube, back to the center. And if the beams are perfectly split and the joining is perfect and there's no distortion in the length of either mirror, then they'll cancel each other out. They'll do a phase cancellation and you won't have any light coming out the bottom of the convergence. The moment that one of the tubes gets a little longer or a little shorter than the other tube because a gravity wave moved through the observatory, then you'll get distortions out the bottom of the convergence, and they'll appear as light and dark patterns because it's monochrome. It's just measuring the amplitude variation on the merge. So that's how they currently measure gravity waves, or GW, and they measure them at low frequency at the 10 to 100 hertz. And the reason why they measure it at this specific wavelength is it's the travel time of the light down the couple of kilometers, which is a very short distance for the speed of light. So that's how come they can only measure these low frequency items, because they emit the beam, and the beam, relativistically speaking, doesn't go very far before it comes back. So that's the wavelength they can determine. If they wanted to determine shorter wavelengths, more little ripples, then they would have to have tubes that were very much longer, like thousands of times longer, so that the light travel time down the tube and then back was very much longer, so it could detect very much different variations. Or they'd have to do something equivalent to having very long tubes. And that's where this comes in. So if the distance was massively lengthened, then the duration of the travel time would be such that you could measure different kinds of gravity waves. And what they're doing is, if you calculate the amount of time it takes for the pulsar to send the energy from the location of the pulsar to your radio receiver, that's called the radio signal time of arrival. And the pulsar spins and it has two jets. So if it's spinning with two jets on it, you get not just one pulse like a lighthouse, you get two pulses. So you're getting them at twice the rotational speed. There are a few 1+ second rate pulsars, but most of them are small fractions of a second. And some of them have very tiny fractions of a second on the time of arrival. These are called millisecond pulsars. And these are the ones we want to use for gravity wave analysis, because if it's a very long duration that the pulsar takes, then a very short disruption in it won't even show up. But if it's a very short duration pulsar, then a small change will make a big distortion in the time of arrival. So that's why they need millisecond level pulsars. And they need to constantly monitor them. You can't be like, well, we'll do it 4 hours a day. Well, what if, a gravity wave goes through and you aren't there to hear it? If a tree falls in the woods and you weren't there to hear it, did it make a sound? Same kind of thing. But you also have to accommodate noise in the signal. So when the pulsar is rapidly spinning and it emits a wave towards the Earth, you get a Doppler shift effect, so that you get the high frequency part of the signal first, and then as the beam energy sweeps through your location, you get the low energy last. So you have to accommodate for Doppler shift, as well as the travel time of the photons, of the flux. Plus, pulsars can undergo their own internal and external stellar disruptions, what they call star quakes, where you have a little shift in the surface texture of the pulsar, and this could be, actually just fractions of a millimeter, but given the density and the large gravitational influence of the pulsar, it can produce a disruption. So you have to know how to filter those out. They went through the same thing with Ligo and VIRGO. There were a lot of things they had to filter out, like, was that a gravity wave? Yeah, that was just somebody driving by one of the tubes in a heavy truck. I thought they were isolated. Well, if you're trying to measure something that's 1,000th the thickness of a human hair, a truck driving by outside your evacuated tube is still going to affect it. So they have to filter out a lot of things for Ligo and VIRGO, and the same will hold true for the pulsar timing array. I'm sure for the next few years, they're going to be finding things that are, oh, we didn't take that into account, have to filter that out. So even though they might be monitoring the time of arrival of all these pulsars 24/7, they may have to throw out a lot of the observations due to signal to noise ratio. Oh, that was noise, throw that out. Hey, we finally got some signal. No, that was just another kind of noise.
Well, but they can compare with VIRGO, so that's where they clean out the noise.
Well, if VIRGO cannot detect a millisecond level a nanosecond level disruption, then you won't be able to confirm it with either VIRGO or LIGO. But if the pulsar network is picking up a low frequency gravity wave, then yes, you'll be able to get corroboration from VIRGO and LIGO. So here's what it looks like. So on the left of the dotted line, you see the Earth, and I've got 5 pulsars. And I didn't want to get specific down into the what the actual duration is of each one of the pulsars. They would be different by small amounts, but they're all millisecond level pulsars, and they're all continuously spitting stuff at Earth, and we're picking it up with our radio antenna. And all of a sudden, a gravity wave goes rippling through, and it affects the timing of P2, P3, and P4, but it does not affect the timing of P1 and P5. This lets us know several things. One is, if it hits P2's time of arrival first, and then P3, and then P4, we know it's going from P2 across over to P4. And if it does not affect P1 and P5, we know that distance from the Earth, it's out farther than P1 or P5, but not farther than P2, P3, or P4. So if you want to do this really well, 5 pulsars is not even a bare minimum. You need maybe 30 or more pulsars to get a good solid set of data. And currently they're out to about 100 pulsars. So they're building a legitimate large scale timing array here.
Okay, so the gravity wave doesn't actually have to hit the Earth.
No, it doesn't have to hit the Earth, and it doesn't have to hit the pulsars themselves. It just has to pass along the beam path from the pulsar to the Earth. And it will take the very regular pulse timing, and because it stretches or compresses the fabric of space-time, it's changing time. So the pulsar timing will be a little faster or a little slower for a period of time. And the faster and slower are on the billionths of a second difference. So what are the parts of a pulsar timing array? Well, you need a bunch of giant radio receiving antennas spread around the globe because the Earth rotates. And if you remember back to me discussing the deep space network, we had to have at least 3 large antennas spread 120 degrees around the Earth so we could point the antennas out in most directions. But since we don't launch spacecraft to the top or bottom of our galaxy, we launch it out through the edge of our galaxy. We only need 3 antennas on the Earth. But if we want to measure as many pulsars as possible, we need far more than 3 antennas because we want antennas that measure pulsars to the north and pulsars to the south, and the Earth is tilted 23 degrees on its axis. Lots of antennas. They need to be high gain and very low noise, so they probably need to be helium-cooled receivers. And we need to be able to receive signals in lots of different directions. So if the field of view of one of the antennas is fairly wide and it can pick up 5 different pulsars, you need to have a receiver that has 5 channels dedicated to those pulsars to receive them. So not only a lot of antennas, a lot of receivers, and each receiver has to have lots of channels. So you would evaluate the time of arrival of each one of the pulsar samples you receive against internationally agreed time of arrival. And you can look at pulsars we've recently detected, and you'll see that not everybody agrees on that like 4th decimal place of the number of nanoseconds of the pulse. So you have to only use the pulsars where the time of arrival has been internationally agreed or established as a baseline. And you have to compensate for, as I said, Doppler shift of the signal. And you have to filter out other things, variances not due to gravity waves. So there's stuff that can get between the Earth and the pulsar, and you have to filter that noise out. If you happen to be pointing at a pulsar just in time for the moon to go by in its orbit around the Earth, well, you got to take out those samples. So you need lots of antennas, lots of receivers with lots of channels all over the Earth, and then you can start looking forward to doing 24 by 7 by 365 sampling. And when you do detect a gravity wave, you need to store high quality data for future retrospective analysis. Like I mentioned last week, other people may find new stuff in the data long after we find a different way to do gravity wave detection. And there's hidden data that we weren't looking for the last time. And whenever you detect a gravity wave, some of the radio antennas may not be pointed at that set of pulsars, and some of them may not be paying attention for gravity wave stuff. They may be frying other fish with their radio receivers, but they can quickly turn to and receive some observational data. So you need to, as soon as possible, send to worldwide radio observatories to get them to see if they can corroborate what you've received. So what's the timing accuracy? First of all, you want to be working with these millisecond class pulsars, very quick pulsars. So the first millisecond pulsar was discovered in 1982. And remember, you need to measure whatever sample you're taking at least twice the rate at which it changes in order for you to detect changes. This is Nyquist, or NyQuil as some people call it. But that's just signal analysis. So pulsar spin rate. So if these are millisecond pulsars, that would say they spin or produce a beam pulse 1,000 times a second, or need to sample at half a millisecond. Pulsars have two signals, coming out both sides, 180 degrees opposed. So you need to actually sample at twice the spin rate. The spin rate of the fastest known pulsar, which they actually determined in 2021, is 716 rotations per second, or 0.698 milliseconds. They've discovered that at 1,000 rotations per second or faster, the pulsar may actually spin down. Its rotational force is such that it actually disperses the energy of the pulsar by spinning that fast. It literally throws it off, and it will spin down to a rate just under 1,000. And they've also calculated, theoretically, they've never detected this in an observation, but if a pulsar were to spin at 1,500 rotations per second, or about a quarter of a millisecond, the pulsar would literally tear itself apart. It'd be spinning so fast that the differential in the equatorial region versus the polar region would be such that it would make what they call an oblate spheroid to the point where it would rip itself apart. So there is a range where you can say you need to sample at least this fast, but you never need to sample faster than that fast. So 4,000 samples per second is achievable with an inexpensive software-defined radio. Even the $20 software-defined radios that I have can sample at 4,000 samples per second. In fact, I can even set them up, if I time everything properly, to about 1 million samples per second. So samples per second for amateurs, not a problem. The antenna to amplifier gain, the signal to noise ratio, that's also not a problem if you have the right kind of antenna. If you have a very long Yagi antenna that can amplify up the signal strength from the pulsar, then even amateurs can receive typical pulsars. So capturing an unaffected pulsar at this rate is not the issue. It's capturing the delta and the pulsar timing of arrival in the presence of a gravitational wave. So what's the required accuracy to capture a gravitational wave delta? So we've already said, amateurs can capture pulsars. How fast do you have to sample? Well, it turns out if you want to measure that very tiny ripple in the time of arrival, you need to time it at around 10 nanoseconds or less. And no, well, that just sort of threw the baby out with the bathwater. There are no amateurs that have computer system timing accuracy that's less than 10 nanoseconds. It's just too expensive because you start needing cryogenically cooled clock sources and stuff. And no, it's not going to happen. So we'll leave this to the well-funded projects, and also the amplitude of the change. Amateurs will be using 8-bit or maybe 12-bit samples, but in order to detect such a small delta in the signal amplitude, you need preferably 16-bit samples, and amateurs can't afford 16-bit sampling equipment. It's just multiple thousands of dollars for them, and then it costs multiple thousands of dollars for the computer that you plug the card in. It doesn't work over a USB interface. It works over computer bus interfaces like PCI Express. So yeah, until they come down in price.
Is that is no pretty pictures and no funny noises, because that's too fast for, lowering down the wavelength to be audible. So there will be not even interest.
Well, there's certainly not going to be any pretty pictures, because this is a time of arrival signal capture, which is just blip, 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 blip. So no pretty pictures there. I guess you could animate the gravity wave ripple through the array of pulsar detection network. But yeah, certainly no pretty pictures of the gravity wave. But they might be able to do a 3D animation of it. So what are the burdens of data transmission and storage? When you're sampling radio signals, you actually have two samples. So when I was talking about how fast you have to capture it and how many bits you want per sample, you're actually taking two samples for every sample. These are the I and Q channels. And the reason for doing this is they don't actually sample the amplitude of the signal. They sample a phase delta between two signals. This allows them to come in after the fact and determine the signal power phase, as well as the frequency of the sample. And this is a different spelling. The calculation of the power to frequency relationship is called a sample phasor. Not a phaser. No phasers on stun here. It's a phasor. It's just a technical term in case you ever hear it. So if you said, I want to capture 500 million samples per second, 16 bits per sample, that's 4 bytes per sample. That's a massive amount of data to transfer and store per second. So that's 500 million samples per second times 4 bytes per sample, or 2 gigabytes of just raw data. Plus you need administrative wrapper and overhead, about 20%. So about 2.4 gigabytes per second. Now you know where these radio astronomy arrays start storing petabytes per day. And this is more data than you can transfer somewhere over a communications link for post-processing analysis. This is data that you have to analyze on the fly as it goes by. Otherwise, every 30 days, you have a pallet full of disk drives that you bulk ship off to a post-processing supercomputing center to analyze it. But that's no good, because if you're not analyzing it on the fly, you won't be able to detect when you have a gravity wave now and be able to corroborate with other observatories, because if you post-process the data and you don't get the results back for 30 days, it's too late. So it's not possible to store on even solid state drives by connecting that many drives up by a USB. You have to connect them up by a express PCI bus, and you have the radio receiver connected up on PCI bus, and you have the disk drives split into array to array so you can parallel store. So if you've got, 8 channels of data flowing off of your radio receiver, you may have 8 disk drives and 4 disk controllers and 2 channels for your receivers, and it gets to be very expensive very quickly, and that's a lot of data. So as soon as you start talking about a network of these pulsar arrays, they're expensive, they're not cheap. And you may want to target less than full rate and only capture around events. So if you're not capturing gravity waves, if you're not detecting gravity waves, you might want to say, store a small amount of data on a cyclic basis. And if you didn't detect anything in the last day, throw away yesterday's data. I know it's a bad thing to do, it's a bad practice, because you don't know what you're going to find in that data 10 years from now. But do you really want to spend millions of dollars for data that contains no events? So when you detect one, start storing the real data and have a few disk drives to spare. So when the gravity wave stops being detected, you can shut things down for a period of time, unplug all the data, all the drives with good stuff on them, plug in some new drives, turn it all back on, do the RAID array, get it reinitialized, and you're back on the air again. So there will be some downtime where hopefully it's not like earthquakes where you have the big one followed by a lot of smaller ones. So current national timing arrays. There are several throughout the planet. So the North American Nanohertz Observatory for Gravitational Waves, the NanoGrav, catchy name that. It's based in Greenbank, West Virginia, where they have a radio array. Historical data used to come from Arecibo in Puerto Rico until it went bye-bye. So the Nanohertz Observatory really is only Greenbank at the moment. But Greenbank's a pretty big dish, and it has good receivers on lots of channels, but it can only look at one part of the sky at a time. So it's not really covering everything. Europe has their own timing array. It's coordinated and funded by the European Union. They've got a couple of them. Jodrell Bank in the UK. No official word yet, now that the UK has left the EU, as to whether they're still officially a member of the European Pulsar Timing Array. I think the scientists would say, yes, let's find a way to make this happen. Otherwise, you're left with Westerbork in the Netherlands, Eifelsberg in Germany, Mankey in France, and Sardinia in Italy. But that's even too small a number of observatories, and not all of them are as capable, don't have as many antennas or receivers or channels. India has fired up their own. They recently did some upgrades to their giant meter wave radio telescope, which they now call the upgraded giant meter wave radio telescope. Now, meter wave is not long radio waves, but it's still longer radio waves than infrared.
FM.
Yeah.
That's not a typo, is it? Meter wave?
No, it's a European spelling.
Yeah.
Metro wave.
Yeah.
And then you have Parkes down in Australia. Well, Parkes is just one place in Australia. So how do you get more observatories looking at more pulsars? Obviously, you got to glue all these guys together. And that's what they did. They went international. So there is the International Pulsar Timing Array, and includes all those other arrays that I mentioned. Plus, they've decided, well, you take a look at these and we'll take a look at those. And during this time of the day, we'll be looking for these. And during that time of the day, you'll be looking for those. And So they've reduced the redundancy of different arrays from different nations observing the same pulsars. That allowed them to spread it out. So instead of about 30 pulsars, they are now tracking over 100 pulsars, which is good news. So the goal of the International Pulsar Timing Array is, as often as possible, receive the time of arrival of at around 100 10 millisecond or shorter pulsars. Compare their time of arrival, conclude whether or not you have gravitational wave influence, compensate for Doppler shift and filter out any other false detections. Compare them across the startup differences to all tracked pulsars in the array to ascertain a plausible gravitational wave source location. Communicate with all the other members to get more precise source location. And once you have that, also turn on other observatories, visual, infrared, ultraviolet, X-ray, gamma ray, whether they be on Earth or in space. Get them all fired up, looking in the direction of the gravitational wave source to see if there are other clues associated with the gravitational wave. And obviously do continuous recording and analysis of all this data and store it all. So more observatories, more observations across as many pulsars as possible is the key to success of the EPITA. So what are the constraints of pulsar timing arrays? Well, obviously the Earth rotates and it orbits the sun, and therefore there's sometimes you can't look there because you can't see there, something's in the way, or there's a giant radio noise source called the sun. So some radio stations can receive during the daytime, others can't because they're on different frequencies. And you can't dedicate full-time all the PTA members to pulsar timing. Those antennas are too critically useful. They may have to be used for other things. So not all stations can monitor 24/7, 365. You have to evaluate what's the cost of sharing, what's the operational staff availability, and for some of them, what's the weather like at that time. Some are limited by how many frequencies, how many channels they can simultaneously receive. So while Greenbank might be able to pick up 50 pulsars simultaneously from a location in the sky, Jodrell Bank might only be able to pick up 3. And you need to reduce the redundancy. So don't everybody go looking for the same pulsars. And they need to be in different parts of the sky. Remember how the arms of LIGO and VIRGO are L? You need to spread out which pulsars you're looking at across the sky so you get better variance of where the gravity wave is moving through and at what angle. But what about gravitational waves in historical data? We've got radio astronomy observatories, and they've been monitoring time of arrival of pulsars for a long period of time. The problem is they may have the pulsar data, but they don't have the variances at the nanosecond level to determine the effect by a gravitational wave of high frequency. So the data may be there, but the quality may not be there, but it doesn't hurt to look. So what has the International Pulsar Timing Array detected so far? Well, first of all, because they had member nations from different countries, they've actually confirmed that the science works, the technology works, and they've confirmed gravity waves. It's much like the early days of LIGO and VIRGO, when there was a lot of noise that they thought were gravity waves, and until they went back and analyzed it and found out, nope, not yet, nope, not yet. And then when they eventually found it, it was several years later. Well, apparently they've worked on the International Pulsar Timing Arrays for a long enough period of time that in 2012, they actually had a workshop where someone did a presentation on We now have it confirmed by multiple receiving stations that we've detected gravitational wave effects using the pulsar timing arrays. So check, have determined it, but they don't have enough measurements yet to do anything other than a course direction of where the gravity wave is coming from. So they've monitored enough pulsars that they can go, well, this wave came from over there. How far over there? Well, we don't have any pulsars that far over to know exactly which star it came from, or whatever it came, merger of black holes or whatever it came from. And we've also not looked in other wavelengths like radio, other bands of radio, infrared, visual, X-ray, or gamma ray to get a fine resolution on the source of the gravity wave. So, but what they have done is, because they've detected so many of them, they've corroborated the detection of them, they're now thinking that high frequency gravity waves may be ubiquitous, kind of like the cosmic microwave background is always there. If you have the right kinds of instruments, you can always find it. Just look anywhere. They're starting to think that the same thing may be true of there being a gravitational wave background. Now, the thought was gravity waves only come from the merging of black holes, very, very large things, very, very massive gravity events, and that's what we're detecting. But now that they're detecting so many of them, the odds on them all being giant mergers of black holes is getting slim. So infrared and ultraviolet radiation existed and continues to exist long before humans realized that they were there, because we physiologically cannot see in infrared and ultraviolet. And it was only after we postulated of their existence and then create the technology to observe them that we went, oh, look, the sun is always putting out UV in multiple wavelengths. But our eyes couldn't tell that. Well, the same thing was true for the cosmic microwave background radiation until we started putting up satellites like WMAP and WMAP, the follow-on for it. We never realized that the cosmic microwave background is always there. It's been there as long as we've been around, probably longer. And there's lots of sources for it, but they're a long time ago because we're seeing it in radio. Well, it appears to be the same thing holds true for gravitational waves. We physiologically are unable to determine when tachyons are passing through us. We're also unable to determine when gravity waves are passing through us because the effect is so small. So now that we're starting to create technology that will allow us to detect high frequency gravitational waves from lots of different directions, look, there's a background of gravitational waves, but now we have to prove it. So we have to do more and more observing, because there's a lot of naysayers out there. And here's the latest one that I was, I guess, read some teaser article. They weren't postulating it yet, but I'm an amateur. I can say it's just a postulation. So far, what they've been looking at is the stretching or compressing of space-time by gravitational waves, which affect the timing of arrival of the pulsar. So it's affecting the beam distortion on the nanosecond level. But a pulsar beam is what is referred to as a flux. It is power based upon the wavelength or frequency of the electromagnetic radiation. And then there's also, well, how many photons, what density of photons are there in this beam that you just detected? So it's not only the wavelength, it's the power, how much energy is in what you received. And those are fairly constant for pulsars, unless something gets in their way, like dust or an off-angle thing interacting with the pulsar's beam. But once you filter those out, if you're doing gravity wave detection by detecting a difference in the time of arrival, you might also look at the amount of power, amount of flux in the beam that you receive, you may find that the amplitude or the flux of the beam varies more often than does the timing. Because if the timing is different by, instead of being nanoseconds, it's attoseconds, which is 1,000th of a nanosecond, you may not have the technology to detect that. But if the power level fluctuates and you can already measure things in nanoamperes, then you have the ability to measure the power distribution change due to the gravitational wave. So that may be something they're going to eventually figure out on their own, but it's just something I'm postulating at this point. It's kind of, well, if you can't measure the frequency of the light, maybe you can measure the brightness of the light. And as to what would be the source of a gravitational wave background source, where are all these sources of gravity waves coming from? And the first thing that the cosmologists postulated was they're all stellar mass black holes that occurred, collision, turned on, whatever, during the early universe. Okay, pause for a second. If such gravity waves only occurred during the early universe, what is the current source for so many of them? If those gravity waves are moving at roughly the speed of light, the bulk of them should have already passed through, should have already passed by. Because if they only occurred during the early part of the universe, we should eventually hit a point where the number of them tapers off. But we don't see any tapering so far. So here's a thought. It's well understood that black holes are a huge source of gravity. That's why they think that when black holes merge, that's where you get gravity waves. Black holes spin rather fast. When a black hole is spinning, it creates an equatorial bulge. Now, the bulge may only be millimeters, but it creates a bulge. If that bulge is disrupted by new matter being sucked into the black hole, and it affects the bulge height by millimeters, and that's spinning, it could be that black hole spin rate could relate to gravitational wave frequency. Black hole mass changes could also relate to gravitational wave amplitude. And if that's the case, do these dispersions of gravity waves as energy deplete a black hole? Could that be the source of Hawking radiation, more so than the occasional photon escaping from the massive gravity of a black hole? It may just be that the black hole is spinning, and as matter goes into the black hole, the bulge gets a little larger, and so it starts having a shearing force, and the gravitational wave is like ripping the mass around. And that could be the source of this background gravitational wave. But here's another thought. First, we have to determine what's the spin rate of a black hole. If you cannot get light out of a black hole, how do you know how fast it's spinning? Think about it for a moment. As stuff falls into the black hole, the speed at which the stuff that hasn't yet fallen in is an approximation of the rotational spin of the black hole. But it's not precise. It's an approximation. So they can get, kind of a good idea of how fast the black hole is spinning. And they don't have an upper limit at this point, much like they have a theoretical upper limit on the maximum spin rate of a pulsar, because otherwise the equatorial bulge force would basically split the pulsar. They found no such similar maximum spin rate for black holes. And the matter falling into the black hole actually has a drag effect. So there's only so fast you can pull that matter around the outside of the black hole. The black hole may actually be spinning far faster than that, but it's kind of like in a washing machine. The clothes that are stuck to the outside of the tub when the tub is spinning, those are spinning at the same rate as the tub is spinning. But until the water leaves the tub and all the clothes are stuck out on the outer edge, the clothes that are still in water are spinning around in the tub at a different rate than the outer edge of the tub. So the matter that has not yet fallen into the black hole may be spinning around the black hole periphery at a much slower rate than the black hole itself. So what's the upper limit on black hole spin rate? We don't have one of those yet, but someday we may. But if we don't know how fast they can go, we also don't know what the relativistic effects are when matter falls into a black hole. So here we go. I learned a new term, the black hole ergosphere. So when a black hole is spinning, we all know about the event horizon. That's where stuff goes in and you never see it anymore. But even farther out than that, there is this thing called the ergosphere. And you can actually look it up. Because a black hole is spinning so fast, it creates this squished sphere. And you have lobes at the equator that actually create a gravitational source that is higher than the poles of the black hole. So things will more easily get pulled into the black hole along the equatorial band of the black hole than higher latitudes or lower latitudes. That being the case, at the moment where a black hole starts absorbing a mass, it will impact the equatorial part of the black hole within the ergosphere first. Now, we all know that a black hole can take matter in only so fast, and that if it gets too much matter, it'll actually just spin it off, and that's part of these jets at the poles that you get from black holes is, I ate too much. Well, if it's eating not too much, but it's eating enough, then it might create a short-lived bump along the equatorial band of the black hole. Now, by the time the black hole spins around to the other side, that lump may have been flattened out. But while that lump, I'll just call it a nub, exists and it's fastly spinning and its mass and it's on the outside edge of a black hole, that would create a significant gravitational distortion. And if you're looking at a gravitational wave background and you've got how many black holes in the known universe and they're all spinning, the ones that are feeding may be the ones of this gravitational wave background, because as they're feeding and they're gobbling stuff up, a nub gets briefly created every time they gobble up a clump of stuff. And that nub, as it impacts the ergosphere, is producing like a whip of gravity. And that may be your gravitational wave background. Now, for those people that, there's two camps in the black hole community, the hair believers and the hair non-believers. What's inside a black hole further down than the event horizon is only theoretical at this point, obviously. But there's a belief that as the matter gets drawn into the black hole, it splits out, it gets spaghettified into what amounts to long straight hair inside the black hole beyond the event horizon. So that's what they're referring to as hair. And they believe that at certain times, the hair can be disturbed, kind of like if you had hair that was sticking up and you went into wind, the wind would blow through your hair and parts of your hair would move. Well, they're thinking that as matter is pulled into the black hole, the hair closest to where the matter is pulled in is disturbed. And if you have a large disruption of this gravity and it's spinning and it's short-lived, they may be actually your gravitational wave background, but it's postulated at this point. Something to think about.
I think there would be another way for you have like the gravitational wave background would be just the frame grabbing of heavy objects, you know, the black holes of galaxies, all smaller black holes, even like neutron stars, you know, heavy objects. Even Earth has some effect of space-time. So as it grabs, it's actually makes a distortion around the space-time.
Yeah.
And so that would be maybe one way to look at this kind of, because you look in detail inside the black hole, but even outside of any very massive object, it grabs the space-time and makes like a distortion. So like the light is moved on the back. So in the ergosphere, you can actually see the light that's coming from your directions. Like it's like the light that is in front of you is the light that's back on you. So you can see 360 degrees in front of you. This is like really weird to understand ergosphere.
An Einstein lens, yes, an Einstein lens. The difference is, and if you look at what I had here, where is it? This slide talks about the GWB as being continuous. You know, so a black hole would have a continuous gravitational wave coming out of it based upon the spin rate of the black hole. But at the moment, they're not seeing continuous sources. They're seeing a variety of sources, and it's changing. So I don't think it's black hole frame dragging, because that would be continuous. It would almost be like, as a pulsar is a lighthouse of photons, if the same thing were true about black holes, then black holes would be gravity wave lighthouses. As they spin, you would get gravity wave pulses. So I said, well, since they're not saying that it's, you know, continuous pulses, it's just sporadic everywhere. That's when I shifted to ergosphere nubs, because those would be very large, very short-lived, and they would be coming from different sources at different times based upon which black holes are feeding and what they're actively feeding upon. So you would have, you know, different sources of gravity waves all over the known universe. But we shall see. Put a push pin in it. So, conclusions. Existing gravity wave observatories have sensitivity and wavelength limitations based upon how long those evacuated tubes are, and you need to have them very much longer. Pulsar timing arrays offer an improved solution for detection of gravity waves at a variety of wavelengths. Gravity waves have been confirmed as being detected by pulsar timing arrays by measuring the time of arrival variances. Maybe they can also detect them through beam flux variances, but verdict is still out on that. Coordinating an international pulsar timing array makes sense, and we have one of those. It might be possible to uncover historical gravity waves from archived pulsar timing data, so long as the data is of sufficient quality, meaning the signal is, you know, nanosecond level signal captures. The possibility exists that gravitational waves at shorter wavelengths are ever present in the universe, similar to the cosmic background radiation. And we'll just call that the gravitational wave background, or GWB, to go with the cosmic microwave background. And just remember that when human physiology can't detect something, it might still be present. We humans just need to create technology to detect it, and we'll never create the technology to detect something that we haven't first theoretically postulated. And I'll put these links in the first comment once I post the video, because showing them means we have to type them in, But if I put them in the comments, you can just click on the text or select the text, copy it out, and drop it in your browser.
What I found really cool about, detecting gravitational waves, that since LIGO and VIRGO had the detections, it completed almost 100 years where the hypotheses and theories about gravitational waves were formulated. It took 100 years for us to actually first detect that. And then what is really amazing, really cool about it is that before, maybe 5 years ago, the only thing we could observe in the universe was electromagnetic waves. So that's our limit for what we could observe and interpret in data. From today, that people even understand that, it's very common. There's apps on the phone that do the monitoring of the gravitational waves. It's becoming ubiquitous that not just you can observe the universe in the electromagnetic waves, but you can also use another way. So it's almost like we only could see in black and white, and now we add maybe sepia color. So we have one way to look at the universe, and now we have another way to look at the universe. So this is amazing because that's opened up for us to understand the universe, even like older universe than we have a limit. So I'm talking about that because when you think about the microwave background, that's the limit what we could observe in the universe. Earlier than that, we are blind for it, because before you could only look at whatever was emitted by the point when the atoms came together. So just like the few 300 million years of the universe was way too hot for having atoms being completed. So the whole universe was plasma soup. Then it stretched far enough that it became cool enough for the atoms coming together. So the plasma cool enough for those photons to arrive here where we are. So now that we are seeing the microwave background, that microwave background was emitted, almost 13 billion years ago in gamma rays. And as the universe stretched, as the time passed, now we are receiving that background of the universe in microwave and infrared. So that's the beginning of the universe, the beginning of the first atoms. So there was a period between that date until the formation of the first stars, what we call the dark ages of the universe. There was no electromagnetic wave being emitted other than the leftover from the microwave background that back then was ultraviolet. So that wave came through us as the stretch is still coming. But then there is a period that we look between that emission of the microwave background and the formation of the first stars. The universe is totally in darkness. And then with the advent of the beginning of you being able to see in gravitational waves, that is a possibility that the dark ages of the universe, where something could be happening, the formation of the first galaxies, even a clumping of matter, even though it was plasma, there was clumping of matter. And then right after the plasma cool off to make, no stars, just mass, there's just gases. And then they start clumping together to form the seeds of the first stars, seeds of the first galaxies. This is totally invisible in electromagnetic waves. But now that we have one more tool, we open one more window to actually see nature. So I really like with the discovery of how and now we have arrays. You can point out the direction, not just see the wavelength. As LIGO and VIRGO could only see the wavelength of those waves and the timing and how much stretch, what kind of energy. Now we are having so detailed, like even LIGO and VIRGO are being updated now we start to giving directions what that happened. And now we can see a little bit more detail. So this is really fascinating. And now with this kind of array that I kind of read about very fast, but I didn't know it was so detailed and so well already established. So now we might be able to see, you know, the formation of the first galaxies, even though it didn't have stars, or those first stars would not have energy enough to arrive to us that early. So this is really amazing, really amazing.
Well, I think of gravity wave analysis as if you consider that ultraviolet, infrared, radio, and visual, they're all forms of electromagnetic radiation, and therefore they're all kind of the same tool. But gravity waves are different. They're a different, not a different spectrum, but a different thing that we're measuring. They're not directly related to one another. So when we were looking in visual and we added in ultraviolet and we added in gamma, those are all still electromagnetic radiation. But gravity waves are not a part of the electromagnetic spectrum. The frequency that they can occur at is akin to the electromagnetic spectrum. It's a wave function, but the actual gravity wave itself is not a component of the electromagnetic spectrum. So I look at it as the EM spectrum, all of it, radio, infrared, visual, ultraviolet, X-ray, gamma, those are all EM, and gravity waves are different, much like the EM is one thing and acoustics is something else, but they have similar waveforms. So I think of
acoustic is the word, yeah.
Yeah, acoustic, it's a different medium, it's a different, it may have wave characteristics, but it's a different thing. So I think of it as if we currently communicate only in the electromagnetic spectrum, and we find there are shortcomings of that, if you had the ability, if you created the technology to modulate gravity waves, you would overcome a lot of the shortcomings of the electromagnetic spectrum. So as I've often said, how come an ET doesn't phone home via radio? They gave up on using radio a long time ago. They're modulating gravity waves. So now that we've discovered that there is a cosmic gravity wave background, what is the modulation technique for that? I don't know. We have to figure out how to receive it and how to modulate it. Because remember, our early attempts at modulation was Morse key. The amount of information passed per second was extremely low. Nowadays, that we can communicate at the gigahertz level, the amount of data per second is very high. But we have a limit when we want to go out to deep space because dilation, space noise, all these things affect it. So if you look at the data transmission rate to the James Webb Space Telescope, its maximum transmission rate is 28 megabits per second. But when you look at the slowest transmission rate to the New Horizons probe that went out to Pluto, it was not bits per second, it was seconds per bit. So the data rate was very much slower to stretch out the signal so that it would be less affected by distortions in space. Like that.
Monroe, are those black hole nubs speculation, or have they been somehow observed or detected for sure?
You cannot determine what's inside of a black hole beyond the event horizon. So a nub would be right at the edge of the event horizon, and we don't have anything that's capable of detecting that. What
right now at this moment is a hypothesis.
Yeah.
It's not even a theory, it's a hypothesis.
Even the hair inside of a black hole, inside of the event horizon, is also a hypothesis.
Yeah.
So that is the old saying, whatever happens in the event horizon stays in the event horizon.
But also, if it weren't for the fact that long ago, people postulated gravity waves, we would have never researched them, created the instrumentation, and detected them. And now that
In
we've
that
detected
case, it
them,
was in the gravitational wave theory of gravitational theory of Albert Einstein. So this wasn't a hypothesis, wasn't just a postulation. It was actually a theory, a gravitational theory. So
How could it
it's
be-
a little bit more, advanced than just a postulation, just a hypothesis.
except he had no observational evidence of gravity waves.
Math is the power.
You need observation because math can be wrong unless you believe silly string theory needs more than 10 dimensions. Yeah.
It's 11.
No, it's 13 if you listen to the theorist. 13 is the current number.
Okay. I
10
need to
was too, 10 was not sufficient. Everybody lost faith at 11, but the theorists are out there at 13. So you can have theory, but theory can have holes. But until you create the technology to actually have the empirical evidence, the data, it could all change overnight, because once you realize it, oh boy, were we wrong about that? Kind of like, hey, at one time galaxies were nebulas because we didn't have the clear enough images to go, wait a minute, that's a spiral. It was just a glowing blob. So I'll stick with, it's safe to say it's a postulation. But
Yeah,
then again,
the other thing is when, not related to what you're talking about, but related to the misnomer of what people use on. So I'm watching videos on YouTube or people talking on TV, and they say, oh, it's only a theory. I'm like, this is a hypothesis. I go like watch the video, hypothesis. Like even scientists that I'm observing and listen to them, it's like the habit of the language that you created, a bad habit of a misnomer. So when I was teaching physics and chemistry, I used to say to my students, I'm going to teleport with the physical science book and I'm going to hit your head and disappear again. If you say hypothesis, or if you say theory instead of hypothesis, I was talking something like this and they go, theory, I grab the book and hypothesis.
gravity is the law, but we don't know what it comes from.
Right.
Something else that is different. So
Yeah.
hypothesis,
So-
postulations, like an idea. So you get a postulation, and then you formulate a hypothesis, and from your hypothesis you can confirm a theory, because a theory is only observation. There is
Yeah.
nothing else. It's just you observe something and you find the mathematical expression of that theory, but it doesn't give you the explanation why. The explanation why is the theory. The theory explains, whatever you observe. It tries to explain why that happens. So that's like some stuff that drives me bonkers, that people, mix hypothesis with theory. Hypothesis is just like you say, it's like safer, as you say, postulation, because it's way much safer, and then you don't get the accident to just use hypothesis instead of theory.
So if you watch Sabina's videos on YouTube, she's a noteworthy physicist, and she's got a YouTube bait video out there right now that says, are earthquakes caused by wind? And she gets right out, her toes are hanging over the edge of her surfboard, right out at the front edge of how this could be the case. And what it turns out to be is, now that we know that things affect the spin of the earth, and now that we know that crystals can be affected by energy, and we know the inverse relationship between, if you vibrate a crystal, it produces energy, and if you apply energy to a crystal, it makes the crystal vibrate. So, the mantle of the earth, all the tectonic plates have lots of crystals in them. So if you have increased solar radiation because the earth is spinning slightly different speed based upon wind on the earth, she's getting way out there to say, we have no correlation yet. So it's only a postulation, but it could be that changes in wind cause earthquakes. Like, okay.
Maybe gravity waves cause earthquakes.
Well, see, that's my belief, is that the super moon itself does not cause earthquakes, but the alignment of the angle of shear force of the water being lifted off of tectonic plates during the departure from perigee of a supermoon. I think you can correlate that to earthquakes. But wind, I'm not so sure.
Yeah.
But until people start investigating
and talk about that, you made me remember my favorite word, syzygy.
Syzygy, yes.
One of my favorite words.
Yes. But much like I did a presentation towards the end of last year on how we detect things, the commonality between electromagnetic radiation detection and gravity wave detection is we count them both by counting electrons. That's the only means we have for measuring anything, is counting electrons. So if I'm measuring light coming into a detector, I'm measuring the difference between 0 to few electrons being captured as a result of the photoelectric effect versus a lot more. So when I look at LIGO and VIRGO and I'm detecting the light and dark areas of the phase distortion, I'm literally measuring the number of electrons coming out of the sensors based upon the photons entering the sensor and creating electrons, and then me measuring the voltage. So
Would you characterize LIGO as an obsolete technology?
No,
I would
really.
say that once we get other forms of gravitational wave detection up and running, I don't think that pulsar networks are the end all. I think they're just another way of doing it. I think we're going to find that as we can make the measurements smaller and smaller with greater precision, we're going to be able to create a gravitational wave detector that fits on a desktop. And
by the way,
that's gonna change
for
things.
those who are interested on LIGO and VIRGO, they have an app that you can download on your phone, and you can actually have the updates of the new stuff, and you can actually see some of discoveries. So they are actually updating their equipment. So before, they could only observe collisions of black holes with black holes. Now they're getting the equipment more sensitive, so they can see collisions between black holes and neutron stars. And also they might update even more the equipment to maybe white dwarf collisions might be detectable with the equipment. So if you can actually look at the app on your phone, they have like the black hole, BB, or they use the letters, and they are already using in the app white dwarfs.
And I'd like to see the same thing for the International Pulsar Timing Array. I went looking for it, haven't found it yet. But I think that LIGO and VIRGO are excellent starting points. But I think that they will eventually be superseded by newer and better technology and smaller technology.
Less moving parts. I hate moving parts.
The only thing that's a moving part inside of LIGO and VIRGO are photons.
Well, the mirror changes, the whole thing.
No, the distance to the mirror changes.
Yeah,
the mirror itself doesn't change.
Well, yeah, that's what I meant.
But they did have a problem when they were trying to work out the false detections of gravity waves. They had updated the lasers that they use to bounce down the tunnels. They upgraded them from a 10-watt laser to a 60-watt laser. They turned the laser on and immediately detected a gravity wave. It turns out that the photons that were hitting the mirror were making the mirror move.
Too small.
Monroe.
Yeah.
Let me just put this pose to the camera so if you guys are interested in that. This is the app.
Chirp.
Let me see. Sure.
Chirp.
Yeah, so I am installed. So it's like you can see the simulation of the collision, and you can also see what kind of collision was that. So it's kind of fun to look. So it's not often because like last time I looked, they were doing the update of the equipment, so there was no new data.
Let's see if I can find it. Because there's usually a website associated with them.
Oh, let me tell you. It is Ligo Caltech edu.
It's out of the UK. It's chirp.sr.bm.ac.uk. That's where the app comes from. I will put that in the chat window. People can go look at it before they figure out if they were going to download it.
Wow, they finished the update. So the last alert candidate, so they call it candidate because it needs confirmation with the other equipment,
Yes.
are 3 to 5 solar masses. So that would be okay. Some black holes will have 2 to 3. But this is like the limit, like the lower limit. This is impressive. Look at how the data looks like. Let's see. Let me move my light and see if that. Oh, overexposure. Yeah, it's over. Hold on. Let me see if I. Oh, okay.
Better.
Sure.
Yeah, better.
I've got a better way of doing it. Give me a second here.
Yes. Okay. So it's cool because when you see the data, it actually shows the direction set. Whatever was detected, the gravitational waves, and they have the 2 detections, and they can see in the world map. And you can kind of have the direction. Yeah, perfect. Awesome.
There you go.
That's what.
So now you can see it digitally rather than analog through a camera.
So
But you can see that they have not just point sources, but they actually have variables. So you can see kind of these cloud shaped, and they're lighter and darker. They're false colored for intensity, and yeah. But they have
and you
event
can actually
information.
see the direction.
Yeah.
Oh, try to click on 3D map. I want to see that. I haven't seen that one.
This sky map is 11 megabytes. Yeah, sure. Why not? It will not work
You're in
with
the
Google
computer.
Chrome on Android. How about Edge? Let's see if it works on Edge. Should take about 10 seconds.
You go, friend.
Well, AT&T bumped me up from 6 megabits per second to 10 megabits per second, and it's frozen.
Oh,
Oh, there it
Oh.
goes. There it goes. Swirly, swirly, swirly.
Thinking.
Don't you miss those hourglass pictures?
oh yes. And then it turns
yeah.
upside down.
I always liked the one that was a dot moving along an elliptical pattern with like a comet tail. Oh, there you
Yes.
go.
Yeah.
Well, mine haven't updated yet.
It's not that thrilling. It looks like
Oh,
a bunch
okay.
of melted licorice candy. And it's changing. Well, I guess they're rotating it.
It's
I'm not moving the
rotating.
mouse. I'm not moving the
Yeah.
mouse, but they're rotating around the
rotation.
axis.
That's pretty cool. That's pretty cool. So as you see in the map that is stretched out, you can see the surface of the Earth. By that, you can actually see that's going inside the Earth. That's pretty awesome. That's pretty
reminds
awesome.
me of the radio transmission pattern maps from antennas.
Yes, that's pretty awesome.
I'm going to go back to 2D because it consumes less resources.
Yes.
It's consuming so many resources, it's not seeing me. There we go. It wasn't seeing me having clicked. So sources. They don't have a source for it.
Oh no, you can see right there on source. they put a probability what it could be. So if you go down, you have black hole.
Gap.
You can have 1%, and then remnant 1%. So as you can see, it's math gap. Math gap means that we're having a weird thing that we can only see very tiny black holes, and we can only observe ginormous black holes inside the galaxies. So they call it the math gap, is the, black holes that we don't really observe, that is in between, that is like a percentual gap that we don't see.
Right.
So they call it those black holes mass gap.
The mass gap is between 3 to 5 solar masses. Which, I don't know, the science of that terminology, I've got a problem with it, because gap is a distance and solar mass is a mass. It's the gap between the masses.
Yeah,
so it should be stellar diameters, not solar masses.
Yeah, but it is really cool that you can actually now getting to the point that LIGO can detect objects that are about 3 to 5 Earth masses. That it's like, it's not massive at all, and the time of the space-time distortion can cause, it's so minimum that's very hard to detect, and it is detecting. So this is pretty impressive.
They'll also give you the status of each one of the observatories. So you got Geo 600, both LIGOs, VIRGO, and Kagra.
If you click on all alerts on the top strip, you have all alerts.
If I can make this go away, there we go.
Okay.
Alert candidate?
No, on the left side, you see SHRP, and then home, latest, all alerts. You can see the list of everything that has been detected historically. So where are the dates? To 2020, 22. Oh no, load more. Okay, so that we can start ahead. And then, as you can see on the top, you can see what they can detect: binary black hole, binary neutron star collision, neutron star black hole, terrestrial noise, and mass gap.
Yep. It also tells you which of the observatories have detected it.
What's the third column?
The third column.
Where it
False
says
alarm rate?
1 per
446 years, 1 per 25.69 million years.
Huh. Interesting.
And it is how often it happens around. They can do a statistical sample, and they can give you.
I think that's literally what it is. It's a statistical sample based upon the accuracy of the detection instruments. So if you said the sensor that detected the phase distortion.
This is the sigma, false alarm rate.
Yeah.
That's the sigma. That's the precision of the observation.
And that's what I was about to say, was that when they detect the phase difference at the back end of the detector, they are using sensors, and the sensors, as I mentioned during the previous presentation about analog to digital converters, they have a variance of how accurate they are over time. So depending upon what they're using for sensing, it may have a very good false alarm rate, or it may have a not so good false alarm rate. So they have to communicate that out per observation. So that's, I think, where these numbers are coming from, because I don't think we have any actual 1 per 25.69 million times the age of the universe.
That's the probability of that being there.
Yes, which I think is more a matter of, oh, they use the expensive detector and its error rate is just not measurable.
It's just like when you have a ginormous storm, right. They call that storm 1 in a million years, 1 in 1,000 years, 1 in 100 years. So they have the probability of that happening.
Yep.
Can you load more to see the first observation so we can kind of,
Well, I just wanted to point out the variance here. Some of the detectors are 1 per 3.39 years. So my guess is that's the
Probably-
cheaper detectors. They're statistically
smaller.
more accurate.
But it's binary
loading more.
neutron star.
How much more do you want me to load?
I want to see
Goes
the
back to
first
2020.
observation. Yeah, I want to see the first observation.
2019,
Was the first one? No.
2019. Looks like 2019. I'm doing load more, and it's just coming up 2019. We're in June of 2019. Let's see if we get earlier than June of 2019.
Oh, keep
Oh, they're
going.
backwards. Yeah, it's International Backwards Day. May 13th of 2019. Why are
Yes.
they doing that?
Because that's normal for everyone else in the planet other than here.
I'll believe that of the metric system, but I won't believe that of calendar dates because there's this little organization called the International Astronomical Union. They use year, month, day because it's sortable. This is not a sortable date.
Yeah.
You have to write special software to sort that. It's not chronologically sortable.
Yeah.
So, okay,
Oh,
so
wow.
we're to April. Oh, I don't see any more. So April 5th, 2019 is their first official detection, and they've classified it as terrestrial noise. So that's not really a gravitational wave detection.
Yeah, and then the binary.
The first one was on April 8th of 2019. It was a binary black hole system.
Yeah.
And then take a look. Black holes, black holes, black holes, black holes. So as you can see,
No, binary
the-
neutron star, binary neutron star. Terrestrial noise. Why do they have terrestrial noise ones in here at all?
because
There's a
They
bunch of
want to
terrestrial
log-
noise.
they want to log, for error's sake.
You know what I think it is? I think they officially log them when they think they've detected them, and then they go back and update the evidentiary data entry to say, nope, that was just noise, but they don't delete them. That's good science. They don't delete them. They just
I like
indicate
it. I like it.
Yeah, it's fine. It's fine.
I like the false alarm rate on that neutron star.
1 per 8 months?
No. There was 1 per 1.13 quadrillion times the age of the
Oh,
universe.
that was
this one?
lovely. That
Yeah.
was lovely. 1 quadrillion times the age of the universe. I cannot even think about that number.
I would say that's an analog to digital converter that they've never in the history of them ever seen it have a bit error.
Overload.
Like-
Well, it's probably because it's like helium
Or-
cooled or something.
50 quadrillion years.
No, 1.13 quadrillion times the age of the universe.
Yeah, so I multiply by 1 in a little bit, so you give it,
Hey, they could be
14.
off by 1. It could be 1.12 quadrillion times the age of the universe. They monkey with those numbers all the time. Or it could be,
That's
instead of being 3,
amazing.
it could be 2.9. I want to see parentheses at the end of that.
They
only go out 2 digits.
So you can actually observe that on your phone, and then when you have the picture, you can see that.
No, I can't. My
Nice.
phone's not that old.
And you can update to 5G. I cannot.
No, I'd have to swap my phone to update to 5G. But in the Fort Lauderdale area, if you're too close to an airport, you may not be getting the higher bandwidth 5G anytime soon.
Right. Yeah.
Oh, look at that, Monroe. The
What?
pink is retracted alert. So
Yeah.
when they are sure it's terrestrial noise, right away they
Right.
log.
Yeah.
But the
that's what I'm
pink
saying is,
ones are
As soon as they
retracted.
detect
So
them, they log them, but they don't delete the ones that they find out later are just noise. They just update the status of them.
yeah, I like it. I like it because they are showing,
That's good science, yes.
the data that's like pure science, the way it's supposed to be. I
Right.
really like the way they did this.
Of course,
app.
they could do better here. So if
Distance
it's
range.
terrestrial noise, that means the noise came from the Earth. How far away was that noise? 34 to 92 million parsecs. I
Hmm.
don't think so.
Yeah.
More like
Well,
miles.
that's why it
or
was
feet.
retracted.
Yeah.
Look at the yellow terrestrial noise to see if that is numbers in the distance.
Yep.
Oh, wow, 200 parsecs. Okay.
But it's terrestrial noise.
Yes. But I like that. I like the way. What is white?
What do you mean? What is
First candidate. What is
white?
white?
What is white?
Yeah, on the tab.
White's
No,
not
there is no-
classified yet. There's no
Okay.
classification for white, so it's
So
not
it's burst
classified.
candidate.
So they
whatever
don't
that
know what
means.
its source is. They've recorded it. I also like, what's the distance? Not applicable or not available. I was like, NA, does that mean not applicable or not applicable or not available? I think in this case, it's not available. And why you
Yeah.
need quotes around not available, I don't know.
Is the way they write things that are parentheses is like,
Because
Acronyms.
it's text versus a number.
yeah, acronyms.
I think Diane's got it right. If I ran all this data into an Excel spreadsheet and I set the format of the
Oh.
column to general, if I just throw the numbers in there, it'll actually do math on this.
Okay,
It'll
yeah,
subtract the distance.
that's right.
But if I
that's
throw
right.
it in there with quotes around it, it'll know that's text.
Okay,
So that may be it.
yeah. That's
Data
that's
typing.
smart.
They're not all using Fortran 77.
Maybe. Look
Maybe.
at the source of the page to see.
Yeah.
Wow, I like, look, like when I installed the app, they only had like 5 observations. Look at how many. I'm shocked because it's been some time I don't look at that app.
I would hope that sometime there's going to be an app similar to that. Nope. Student support funding application. So yeah, they are attempting to create an app for the International Pulsar Timing Array. But
Okay,
they're looking
that's
for
not bad.
money. Do you want to provide funding for it? I think the EU would fund it. Hey, I'm jealous. They've got more people working on the International Pulsar Timing Array than they have looking for near-Earth objects going to hit us.
Yes.
This is more people than work at McDonald's. Nope. Sorry. No app for you. You know,
Not
these,
yet.
these projects don't talk to one another. So it may be that this group and the Ligo VIRGO group haven't.
Oh, take a look on outreach. They have an outreach.
I'm looking at data releases at the moment. Data
I
release.
think if you look on the outreach tab, they might have something that will be more to my
I'm headed
area
there.
of educational stuff. Oh,
You
okay.
get a lot of British school children. No mobile phone app yet. I will look offline for that because I would be very interested to see if they have an app or if they have the data, because I've been known to write an Excel macro or two. So we're coming up on the bewitching hour. Is there
All
anything
right.
else more for tonight? So anything else for tonight's nonsense before I stop recording?
One thing I was thinking about all my life up until today, I thought a gravity wave coming from its source propagates out everywhere.
Yeah.
But you're saying it can go in front of pulsars.
Yes. It can, instead of being omnidirectional, it can be directional.
Hmm.
If I have two objects that collapse into one another and the first side of them that makes contact is where the gravity wave is emitted from, then I'm going to get a directional gravity wave.
I never knew about that. Okay.
Yeah.
Well, it's interesting.
Now, the other thing to think about is the universe is three-dimensional.
At
What's
least.
the difference between the pinwheel galaxy and the sombrero galaxy?
Hmm.
One's facing at you and the other one's edge on to you. So in the entirety of the universe, all the pulsars that exist, not all of them are facing towards us. Some of them, the pulse is not pointed at us, but they still exist. So there's only so many pulsars we can use for our timing array. And it might eventually get to be the small number of thousands, but I've got to believe that there's billions of pulsars out there. We just can't receive them because they're off axis.
The universe is vast.
Yes,
And
Oh,
they're
wow.
so tiny.
yes.
And Monroe, during your presentation, a question occurred to me. So
Sure.
before the first stars ignited,
Yeah.
was there any visible light in the universe?
Before the first stars, would there be any light?
Correct.
Yeah, no, there.
Or anything in the visible light spectrum?
Yes, there would be.
No, no, the
There
whole
would be.
universe is plasma.
There no.
So
There
the
would.
plasma
There
is not
would.
transparent.
There would be infrared light prior to the first stars switching on, because prior to the star switching on, you do have a buildup of compressed gas which would produce heat. So you could have infrared. You might have some radio, but you're not going to have anything visible.
So if you mean like right after the Big Bang until, you know, the microwave background, that would not be possible because plasma is not transparent. So whatever photon gets emitted, absorbed, emitted, absorbed. So it takes forever. So just for you to have an idea how would be the whole universe, imagine like inside the sun, whenever you have fusion and then photons come out to the surface, those photons take 25,000 years to leave the sun, something like that. I forgot the exact number. So it would be like an absurd number of time for one photon that came from the nucleus of the sun to go and cross the whole plasma of the sun for you to actually see with your light the emission of the sun, because plasma is not transparent. So right after the Big Bang until the formation of the first atoms, you would not have light being transmitted in universe. Everything was kind of, imagine that everything would be white, kind of, you know, super
Well,
white.
ask a simpler question. What is light? If light is photons, and the only way you're going to get photons is from electrons, and the only way you're going to have electrons is to have atoms, then yes, you need at least the first atoms to be formed.
Yeah.
But as to whether or not the infrared or radio light would be visible, it's visible from where, by who, with what? So it would be emitted, but visible from where? There's nowhere to be. So yes, I think photons in the infrared and radio spectra would be produced, but they wouldn't be detectable because there's nothing to detect it.
Well, let's say you could transport yourself in time
Yes.
back to then, and you're floating in space and looking
Yes.
around, and it's just pitch black, can't see anything. But don't certain particle collisions produce photons? Or
Only
are
if
those
there's
Yeah,
atoms,
they
only if there's
produced by
atoms and
stars?
only if there's atoms and electrons to make it happen. But
Well,
Well,
during
the earliest period of the universe, it wasn't empty space. It was gas, hydrogen. So it's not empty if there's a large, dense hydrogen cloud that makes up the known universe.
I can
okay,
kind
so
of
let's
guess.
say you transported yourself to 20 years before the first star ignited.
Yeah,
So
okay.
you
So
now have gas and things that have coalesced into
Yeah.
orbs
Yes.
that are out there. They just haven't ignited yet.
So have you seen the Bok nebulas? That they are
No.
totally black. Those nebulas, they're totally black. And then when you use an infrared telescope, doesn't matter if it's land or
Mhm.
space, you can see a bunch of stars inside of those nebulas.
Yes.
So that might be the way. So you would need an infrared telescope to see through the darkness, because that would be a lot of accumulation of gases everywhere. And those seeds of stars would be collapsing. You know, you have the cloud collapse and and the beginning of forming of those stars, that would be what I kind of would guess would be,
Yeah.
you know, the beginning.
Yeah,
That's just my understanding, what I would see if I could transport myself to back then.
as we know it right now, the laws of physics weren't different at the earliest points in the universe's existence. So what we know now of gas becomes dense through static electricity and gravity and heats up and eventually gets compressed to the point where you have fusion and a star turns on, that process would still occur. So the
Yeah.
earliest photon emissions, the earliest electromagnetic radiation emissions would be in infrared and in radio.
But aren't
you
there,
know,
like,
Diane,
is it
you know,
neutrino
Diane,
detectors that look for flashes of light?
yeah, Diane,
Would
but you
neutrinos
know what?
exist?
What you were saying would be about the edge where when the James Webb Space Telescope would be, you know, showing us in the
Yeah.
farthest parts of the universe. That what you're talking about, maybe the formation of the first galaxies before, you know, you have the reigniting of all the stars, you have the re-ionization of the universe, because you have the universe started ionized and then deionized, so those are the dark ages, and then the next phase is the re-ionization. So maybe the James Webb Space Telescope would be seeing that edge of whatever would be visible in infrared. Is not even like, you know, galaxy collapse and cloud collapse form stars. So you might be in the right idea of what the James Webb would be able to
Yeah.
see if we
Just
get detailed picture.
Just remember, the James Webb can see medium and near infrared. It cannot see far infrared, which is close to radio waves. So there are already radio telescopes that are looking farther back in time than the Webb. And what they've seen is just raw emissions of radiation. They don't have structure to them. I guess the best way to
infrared
describe it,
background has some structure, Monroe. If you
The
see
cosmic-
pictures of the infrared background, not the microwave, the infrared background. So you can compare the infrared background with the microwave background, and you can see those globs of matter that started to form the first seeds of galaxies when the universe was a little bit closer together. So this is like, you know, the beginning of the actual expansion. So you can actually notice some stuff too if you
as
look at the
galaxies, yes, but as stars that are precursors
It's
to a
hard.
galaxy,
because it's
no.
too far away. Yeah,
right.
it's too far away.
But we might in the future when that light finally makes it to us.
Well, we could look far and back in the past with
Yeah.
the James Webb. Because like if you compare, the Sophia can see on the far infrared, but the thing is that Sophia is a very small telescope compared with the James Webb telescope. So we might go to the really beginning of the universe with the James Webb telescope. So that
Now,
would be interesting. The
We
first data
we
that's
can
coming
certainly
up.
look back further, but we can't look back as far as we know physics should be able to take us,
Sure.
because the Webb cannot look deep into infrared. It can look near infrared and mid infrared, cannot look deep infrared. It doesn't have the instruments for it.
But we would look a little bit back then. The
Yes.
Hubble Space Telescope.
You
and
can
the
look
other
back further,
telescopes. Yeah.
Which is why you have the W
That's
first.
when you go to far infrared, you need a even larger telescope.
Yes, which is why you have LOFAR. The next generations after Webb, you have two of those, and they're very much like the Webb makes Hubble look small. The LOFAR telescopes are going to make, not the LOFAR ones, the Voyeurs. The Voyeurs are going to make the Webb look tiny. How they're going to get them there, we don't know yet.
No, how they would build the thing like that and put inside the spacecraft, that would be like fascinating.
I think we better count on Elon building us a rocket and we'll assemble it in space.
Sure.
Sure. That would be awesome. Assemble a telescope in space. That would be awesome. I would.
Who's-
Me. Can I put together too? Can I go? You know, be a
Yeah, it's
constructor?
like Legos and super glue. Yeah, we'll put it together in
Yes.
space. Yeah. Anyway,
Anything else?
anything else? Because we're still recording at this point, so I have lots of meaty things to add. Okay, then. We'll talk again next week. Anything comes up in the meantime, let me know. I'll edit this and post it to the YouTube site. And then next week, we'll talk about two bodies. Two bodies walked into a store and they orbited.
They walk into a bar.
Yeah.
Yes. Bye. Have a good night.
Good
to all.
night.
Good night, everybody. Thank you. Take care.
Bye.
Good night. Thanks.